So where we ended lecture on Thursday was looking at nucleophiles, and one of the things that we talked about that's a little bit difficult to play around with is looking at these kind of last two sections of nucleophile strength. Okay, so there is a solvent dependence, which we're about to look at in more detail, and then we also have steric hindrance, which we're going to look at in a little bit more detail as well. Typically those aren't tested on, at least 4 is not tested on. The steric hindrance does get tested on. So they aren't as critical to have strictly stuck in the back of your head and memorize, be looking at every single time. Whereas the first 3 rules, super important. You need to be looking at those every single time. So let's take a closer look now at rules 4 and 5. So if we now jump into taking our nucleophiles and dropping them in a solvent. So the first thing we should try and do is do some interpretation of these figures. What solvent are we looking at in the first one, and what solvent are we looking at in the second one? Well, hopefully you can recognize the first one. What we're looking at is water. Let's actually not write the formula. We've got water as a solvent, which happens to be our polar protic solvent. Okay, I can spell protic correctly. We've got our protic solvent. In the second one, we're looking at acetone, which you may or may not remember at this point. Eventually you will recognize that structure. And acetone is polar aprotic. So really the only thing I'll note is the big difference. So we're looking at protic versus aprotic. So what differences come out of this? Okay, so let's start looking at the protic environment. So in a protic system, we're looking at now relatively strong interactions between our negatively charged species and our solvent. Okay? And in this case, we're looking at a solvent that has very large partial positives. Okay, so this is one of the benefits of a protic solvent, is we've got these big positive, partial positive charges and these big partial negative charges due to the electronegativity difference. So that's pretty huge. In this protic environment, we now can look at between the chloride and the bromide. And one of the things that we'll notice in trends is that, yes, bromide gets bigger, but chloride gets a lot more electronegative, which means in the case of chloride, you have now condensed that negative charge into a smaller area. Okay, well, the smaller that area is for a negative charge, the more reactive it becomes, the more it can be stabilized by a partial positive charge, in fact a large positive charge, by the solvent. So what ends up happening is in that protic environment, the smaller your nucleophile, the more stabilized it becomes by the solvent. Well, that could be a bad thing, because if it becomes stabilized, it's no longer a good nucleophile. We've actually made it a weaker nucleophile. So we got to watch out for that in our protic environment. When we go to the aprotic environment, we still have that kind of polarity associated with, say, our oxygen, in this case, and our carbon. But as we'll find actually on the next slide, that carbon, that positively charged carbon, is actually buried in the middle of the structure, which means it doesn't quite have a strong interaction with the nucleophile. So we're looking at a relatively weak coordination between the solvent and our nucleophile. So then the question becomes, okay, well, how does that change my interactions? Well, since the nucleophile is relatively small in the aprotic environment, what ends up happening is that it interacts with very few solvent molecules. But bromide, being larger, much bigger, interacts with a lot more solvent molecules. So if we're trying to consider how does that nucleophile go through and react with something, it needs to break away the solvent molecules so that it can react. Chloride, interacting with very few solvent molecules, now we only have to break one solvent molecule interaction away for chloride to react. The bromide, on the other hand, has more solvent molecules around it. We'll have to break more of those solvent interactions away, so that ends up weakening the strength of the bromide nucleophile because it has more stuff around it. So we end up getting a weaker nucleophile there and a weaker nucleophile there. So we get opposite trends coming out of this because of that solvent effect. And because I will freely admit this is a confusing topic, I want to make sure that we actually got this right. So in the protic environment, we are looking at our larger atom being more nucleophilic. In the aprotic environment, we're looking at our smaller atom. Whew. Thank goodness. So yeah, we got that right. The next thing to watch out for is that if you have no solvent, okay, so if we're not specifying a solvent, bigger is more polarizable, meaning the electron density in that larger structure can shift over a larger area, and it can potentially become more nucleophilic. So in a standard kind of condition, overall results, in general, the bigger your nucleophile, the more nucleophilic it becomes. We can have this weird solvent effect pop up, fairly rare, but it's something to be aware of. Just kind of watch out for it. And it most commonly shows up when you're looking at negatively charged nucleophiles. So the next issue that we're going to encounter here is this concept of a nucleophile versus a base. Well, they do have different definitions, but the definitions are pretty subtly different. Your nucleophiles donate electrons to anything other than a hydrogen, and your bases donate electrons to hydrogen. So both a nucleophile and a base are going to be negatively charged, or at least have some source of electrons. So how do we decide, is it a base, is it a nucleophile? Well, that's kind of a challenge. It turns out that sterics play a pretty big role in this reaction as well. So if we take a look at a substrate that we've got set up here right in the middle, and so we've been using blue as substrate, and then we've got our nucleophile and or base over here. Okay. This happens to be a strong one. Why does it happen to be a strong one? Well, this was off of one of those earlier slides. It's negatively charged. So we've got a strong nucleophile and or base. For it to act as a nucleophile, that negative charge must come in and attack that carbon. For it to act as a base, it has to come in and attack a hydrogen at a beta position. So we'll pick that hydrogen because it's most accessible right now. So what is the difference between these two types of reactions that would allow us to then say something about our nucleophile or base, our negatively charged species, to say which is going to be preferable? Okay. Well, it comes back again to those definitions. Let's think about our nucleophile definition. We have to have it donate electrons to an atom other than hydrogen. Well, that atom most commonly is carbon. Where is carbon found within any structure? I know it's kind of a weird question, but think about it a little bit. Okay. Carbon is found in the middle of a structure. You'll notice that carbon always has 4 bonds. So there's always 4 things around that carbon. And those things all have some form of electrons. So for our nucleophile to attack a carbon, it has to get by a bunch of other electrons. So if our nucleophile now also has a ton of electrons, okay, or a really big size, that size now starts to prevent the negative charge from getting into the center of that carbon, okay, because it's got to get by all that other junk that's around it. If you think back to the SN2 mechanism, remember we said we couldn't attack from the top because the halogen was in the way, our leaving group. Okay, so we had to go in from the backside. Well, how is that different from a base? Well, what does the base donate electrons to? The base donates electrons to a positively charged hydrogen, and hydrogens are always found on the surface of your molecule. This means hydrogens are much more readily accessible or available, which means we don't care what the size of the base is for at least a first approximation. And that's because it's attacking hydrogen that's readily available on the surface of the structure. So when we go through and we're trying to decide, do I have a nucleophile or do I have a base, one of the tip-offs can be something to do with size. Okay? And it's kind of an odd one, because nucleophiles are typically very small. Okay? They need to be small to get in to attack that carbon. Bases, it doesn't matter. So in this case, with this structure that we've got drawn here, or this potential nucleophile or base, we've got ourselves kind of in a pickle here, because it can act as both a base and a nucleophile. Because it's small, it can act as a nucleophile, and because it's negatively charged, it can act as a base. Sterics doesn't prevent it acting as a base. Sterics prevents it acting as a nucleophile. So it's kind of those weird conditional ifs in our system. So if we were going to be nice and we wanted to very clearly say, hey, this is acting as a base, what we would need to do is change the structure. And what we could change the structure to would be something like this guy. This guy now has a whole bunch of sterics on the back side of that negative charge. That steric interaction will now prevent this from acting as a nucleophile. So it cannot act as a nucleophile. If it can't act as a nucleophile, we're then relegated to it just acting as a base. And we now have a system on how to define this as a nucleophile or a base. So that's a common one to show up. The other name that you might see in reference to this would be T-butoxide. So here's your oxide, and then this piece is your T-butyl, okay, which can sometimes be conditioned down to T-butoxide. So you might see T-butyl oxide or tert butoxide. All those names are perfectly valid. So we got one more little structure here to show. I want you to take a look at that molecule and decide how should it interact. Okay. First off, is it strong or weak? Is it a base? Is it a nucleophile? And then where is that nucleophile or base characteristic within this molecule? It's kind of a trickier one. It involves a lot of different concepts. So think about that and be free to ask that in class or in office hours. So common nucleophiles, you'll notice that in our nucleophiles, one of the fairly common trends that we've got for these is they're all relatively small nucleophiles. Okay? And these are all going to be negatively charged, which makes them all strong nucleophiles. We do have neutral nucleophiles that could potentially show up, they just aren't as strong. The last thing that's noted kind of on the bottom there is you'll notice that in these lists we have the chlorides, bromides, and iodides, and those, interestingly enough, can only act as nucleophiles. Okay, the reason being is if they act as a base, they have to react with H plus to make, say, HI. As you should remember about HI, HBr, and HCl from 151 or your general chemistry class, those are strong acids, and by definition the strong acid completely dissociates into the ions, which means we can't have any of the halides act as bases because they form a strong acid, which by definition can't form. Okay, so kind of some neat things that can come out of that on what you might see for your nucleophiles. So now what we're going to do is tie this back to the reactions. So we've got our SN1, and we've got our overall mechanism, and now what we want to do is consider how do each of these effects or each of these conditions potentially play into the mechanism. So the one that we just ended on was looking at nucleophile strength. Would I expect an SN1 reaction to care about the strength of the nucleophile? Well, we could look at this and try and decide what's going on, but I mean, the nucleophile shows up, so we want to change our perspective a little bit. This is where it's important to look at the rate law, which I think I have on here, yes. And when we look at the rate law for our experiment, all we're concerned about is that slow step. And when we look in the slow step, the nucleophile is not present. The rate is not dependent on the strength of the nucleophile, which means I don't want a strong nucleophile for the SN1. It has no effect in my overall reaction, so who cares? We'll ignore the strength of the nucleophile, which means if you're going to look for nucleophiles in a substitution reaction, we want to see a weak nucleophile. If we continue to work our way backwards, I think we move into the solvent effect. Okay, well, if we look at our solvent, okay, what does that solvent need to do? Well, it again is involved in that first step. I'm trying to transition in that first step. How does the solvent potentially help? Okay, well, one of the things that we need to have happen is we need to form a carbocation and we need to form the leaving group. Both of those things need to occur before the nucleophile can come in. So that means I need the most stable positive and I need the most stable negative for the reaction to occur. So how can I stabilize that positive charge? Well, I need to put it near some other negative. And that negative should be as big as I can possibly get. Can the solvent contribute a negative? Well, if we dropped in, say, water, we end up with a very large partial negative charge. That negative charge can help stabilize the carbocation. Well, the more stable the carbocation, the faster that first step goes. So cool, that works. What about the leaving group? Well, if we used water again as a solvent, I have a very large partial positive charge from our hydrogen. I can again stabilize that leaving group. So a protic solvent is a pretty good solvent for an SN1. If we move to an aprotic, we aren't stabilizing the cation and the leaving group as well, which means our reaction isn't going to occur quite as fast. Okay, so protic solvents work out really well. And yes, we'll talk about and summarize this in a second. Leaving group ability, we just talked about one way to stabilize the leaving group. Ultimately, the leaving group, we need one, so it's not that big of a deal. As long as you can see that you have a leaving group, you're going to do it. This is a potential reaction. The last part is looking at the substrate. So the substrate at the beginning doesn't do much, but at the end of that first step, we form a carbocation. So when I'm looking at speeding my reaction, I want to make sure that carbocation is as stable as possible. Well, what substrate is going to stabilize a carbocation best? Well, one that is tertiary will stabilize the cation best. So we're still going back to our reaction, and in fact for this reaction we end up ignoring all of the rest of this reaction. All we're concerned about is that slow step and what things we can do to speed that step. And that's really what we're trying to do when we think about these four things. Okay, so substrate. First thing we do is we form a carbocation. So we have to know what makes our carbocation stable. This was one of the analyses that we keep coming back to. Our carbocation is more stable as a tertiary because there is more electron density in the tertiary than in the primary. So we could make the argument that there's only 6 electrons here, and we can make the argument that we have 4, 4, 4, 12, 12 and 6, 18 electrons here. So 6 electrons from the bonds, and then the valence electrons from each of those carbon atoms. Okay? And yeah, it's a very hand-wavy argument, and your counting of electrons can come up with slightly different amounts, but either way, any way you count them, you will always find your tertiary has more electrons. And the effect we're looking at here is kind of a secondary effect. We aren't really doing any electron pushing, we're just saying there's electrons nearby, those electrons are close enough to stabilize it. So it's kind of a weak argument, but it works. But what about the rest of these alkyl halides? Well, the rest of these alkyl halides, we now need to evaluate the stability of the carbocation. So what we should go through and do, and I'll do it for the first one, you can do it for the others, is we should go through and remove the halogen, put the positive charge on, and decide, is that halogen resonance stable, or is that carbocation stabilized somehow? So in that first case we might say, oh, that's primary, that's horrible, that can't possibly work, except we have a resonance effect And that resonance, I'm going to change my arrow now, goes through and it puts the positive charge on a different atom. This means that the originally charged carbon has less positive characteristic, which means it is more stable, it is less charged. Okay, so that means that that one should be stabilized, and if it's stabilized, we would expect an SN1 reaction to occur. Okay, so it ends up being even more stable than a tertiary carbocation. As a general ranking that can come out of this, you'll notice, or what we've got at the bottom there is a tertiary allylic. Okay, allylic is just in reference to where your carbocation ends up forming. So our chemistry occurs here. It is a sigma bond, then a pi bond. Okay, sigma pi, we're looking at an allylic position. So tertiary allylic is more reactive than secondary allylic, more reactive than primary allylic. Depending on who you talk to, what rankings, what lab experiment you've run, the primary allylic can be very close in reactivity to the tertiary alkyl halide. Either way, it should be more reactive than the secondary. One of the other things that you might note on this list is that I did not mention primary or zeroary. And the reason being is that those carbocations are so ridiculously unstable that we can't form them for any real lifetime in a reaction. The other ones that I did not include on this, which should become relevant as you go through and work those problems I told you to work, did not mention sp2. Okay, when we're looking at all of these rankings, we're ranking sp3 carbon atoms, okay, or sp2 carbocations. What happens if we look at an sp2 alkyl halide? Well, the sp2 alkyl halide is so unreactive as well that we don't ever see that form a carbocation. Okay, so just kind of making you aware of that, and that might help you answer some of your other questions. When we move to solvent effects, again, it's still all about the cation. So what we're trying to do is decide what solvent is going to be best. So if we slowly step our way through it, we either have a polar solvent or a non-polar solvent. Well, polar is going to give us partial charges, okay, a partial positive and a partial negative. Non-polar gives us none of that. Well, that negative can interact with the carbocation, stabilize it. So polar is better than non-polar. We then decide protic or aprotic. Well, protic gives us a larger, so I give away all the answers. Protic gives us a larger partial negative than our aprotic. That partial negative can do a better job of stabilizing the carbocation than the smaller negative of the aprotic. That's why we expect the polar protic solvent for our SN1 mechanism. Okay. So all put together, what we're concerned about is that carbocation. So one of the things that you'll hear me ask a lot is once you've decided it's an SN1 mechanism, you need to immediately be triggering cation. Okay? So when we think back to all of these four conditions, substrate, leaving group, nucleophile, and solvent, you need to be classifying each of those according to, is it leaving an okay cation? Do I get a reasonable cation? So for the substrate, any substrate that can generate a good cation, a nice stable cation, tertiary or resonance stabilized, that's going to be a good thing for an SN1 mechanism. Leaving group. The leaving group should always be good. There isn't more I can really add to that, and we'll find that the leaving group isn't super important to evaluate because all of these mechanisms require a leaving group. Nucleophile. Since the nucleophile is not involved in the rate limiting step for the SN1, I don't care about the nucleophile. So it ends up becoming weak, okay, kind of by default, and we'll talk about why we don't want it to be strong when we move into the next mechanism. Solvent, we want polar protic. It needs to be protic because it can stabilize the carbocation, which this again goes through our whole role on SN1 is carbocation stability. The more stable that cation, the more likely it occurs. Some other kind of things that can come out of your SN1 reactions. Stereochemistry, you do a loss of stereochemistry, quote unquote. You still have stereochemistry in the product, you just have both types of stereochemistry. So you convert to an optically inactive product. So you have racemic products for the most part. Complications within the reaction, you can get rearrangements. And the rearrangements ultimately come from our primary reason that we're looking at SN1s, carbocations. If a carbocation forms, you need to immediately be thinking, can you rearrange? If you can, do it. Then finish out the rest of your mechanism. Okay? So those are your big summaries for your SN1. When it comes to the SN2, for some reason I decided to cram it all onto this one slide, so it's all here. We're looking again at this reaction, we're deciding between those four things: substrate, leaving group, nucleophile, and solvent. So substrate. Okay, what's going to control our SN2 reaction? Well, it's all about that backside attack. The nucleophile must come in and attack the backside of that leaving group bond. Leaving. Okay, well, it's attacking the backside because there's a steric hindrance of the leaving group and the nucleophile button up against each other if it tried to come in from the other side. That's a bad way to attack. So what does that mean about the substrate? Well, the substrate also contributes electrons in the form of the bonds around that carbon. So if we're looking at our substrate, we want it to have as small a backside as possible, okay, or have minimal electrons around that backside, which means we want the smallest or the lowest I guess is a description for it, number of groups around that carbon. So what we're looking at is our primary, or our zero areas reacting better than our primaries, better than our secondaries, better than our tertiaries. So what we would do is classify our substrate according to those rules. So if we saw a zero area, that goes better. Whoops. That goes better than our primary, better than our secondary, better than our tertiary. Okay, you'll notice that we won't be drawing a resonance effect into this one, so we won't be looking at allylic or benzylic. And the reason being, those contribute to stabilization of the carbocation. There's no carbocation here, so all we're really concerned about is these rankings. Can we see an allylic carbon react in an SN2 reaction? Absolutely. It would potentially classify under our primary situation. One of the things that's kind of nice about looking at this reaction is, just like with our SN1, our extreme case does not react. So we expect to never see a tertiary substrate react under the SN2. Leaving group ability, it needs to be good. We already explained that. Nucleophile. Why does the nucleophile need to be strong? Well, if we go through and look at our rate limiting step and our rate for our reaction, the nucleophile shows up in the rate. Okay? The stronger this nucleophile is, the more the effective, so stronger equals a larger effective concentration. Well, if the concentration of your nucleophile goes up, the rate goes up. Okay, so we want a really strong nucleophile to help push this reaction. This was one of the things we were talking about with the SN1. In the SN1, we wanted a weak one. Okay, we didn't want a strong one. We said it didn't matter really, but if we make it a strong nucleophile, we now start to fall under the category of the SN2 reaction. And that's going to be our kind of defining line. So our SN1 kind of by definition gets a weak nucleophile, because as soon as it's strong, we push SN2. Okay? So we'd have to go back and review all those rules on what makes a strong nucleophile. The next part is our solvent. We want an aprotic solvent. Okay, this one is kind of interesting. Well, what's happening in this really comes back to this concept of a strong nucleophile. So for me to have a strong nucleophile, I need a negative charge. Well, what happens if I use a nonpolar solvent? Well, a nonpolar solvent comes in with zero charges. Okay, Well, if I have 0 charges, is that negative charge going to dissolve? Solubility rules say like dissolves like. I get no solubility. Well, that kind of defeats the purpose of using a solvent. Okay, so I need some polarity in my solvent, some positive charge to help dissolve the nucleophile. Okay, so that's why it needs to be polar. But why not go full protic? Okay, well, what happens if we go full protic? Those positive charges now become very large. What does that large positive charge do to the stability of my nucleophile? Well, that should make it more stable. Okay, one of the things that we tend to think about is, oh, more stable is better. Except, what do we want for our nucleophile? We want a strong nucleophile, which is by definition going to be unstable. So if we use a protic solvent, we actually weaken the strength of the nucleophile. The weaker the strength of the nucleophile, the smaller the effective concentration, rate slows down. Okay? So we want that aprotic solvent to help stabilize that. Once we've decided it's an SN2 mechanism by ranking all of these 4 things, we then have to remember kind of our issues that come out of this. When it comes to stereochemistry, we very typically expect an inversion in stereochemistry. So we'd go from R to S, S to R, that kind of fun thing. One of the nice benefits of the SN2 is we don't get any rearrangements, okay, which is kind of nice. Along the lines of our stereochemistry, our benefit is also that we only get one product. In the SN1, because you have a racemic mixture as a product, you get 2 products. Okay? So, pretty sweet deals on our SN2s, sort of. So, deciding between your 2 mechanisms. Well, you need to go through and rank your substrate, your nucleophile, your leaving group, and your solvent. Okay, so what this table does is it kind of summarizes those big bullet points on what you need to know to kind of go through and do it. And you'll notice that the bolds are really your big, strong aspects that are really driving a lot of these. So what you would do is look out for your substrate structure and your nucleophile strength. Those are going to be your big ones. Okay, so if you have a strong nucleophile, click SN2. If you have a weak nucleophile, you're probably looking SN1, but let's push it a little bit further. Look at the substrate. Okay, does your substrate form a stable carbocation? Well, if it does, then SN1 makes sense. Okay. If you really can't tell the difference between the substrate and the nucleophile on deciding SN1 and SN2, the leaving group isn't going to help you because you need a good leaving group. So the last thing you'd have to fall back on is the solvent. SN2 favors the aprotic, SN1 favors the protic. Okay, so all of these things are now contributing to either one mechanism or the other. So you have to be kind of careful when you go through an approach. It's just a process of defining and kind of checking off a little tick mark saying, oh, substrate says SN2, nucleophile says SN2, leaving group I don't care, solvent I'm not told the solvent, so you can't check that. Well, according to those checkboxes then, if we're saying we have 2 possible checks here, and then no information given here, what we're saying is that we have to be doing the SN2. There's no other way we can do the SN1. It's 2 to 0. Okay, SN2 wins. Okay, so that's kind of what you should be thinking through and processing. If you need to, generate a table, which we'll show in a little bit once we bring in the elimination reactions. So, when we bring in the elimination, here's our overall reaction. We could draw out our mechanism and tag arrows across the top of this. Okay, our leaving group leaves. We form the carbocation. Okay, and then what happens is we remove the electrons from a hydrogen. That is typically done using heat. So heat helps weaken that bond in an E1 reaction, and we can form our product. Okay, and we end up with either the cis or trans product, but very likely it'll end up being the trans product as your primary product, as your major product. So what things are going to control this? Well, our rate limiting step says it's the first step. Okay, so in that first step, just like with the SN1, we're forming a carbocation. That means the substrate needs to give me a stable carbocation. So we're looking at resonance, or we're again looking at our tertiary being more reactive than our secondary. Okay. Leaving group, okay, again, should be good, not very helpful. Base, okay, here's a big difference between our substitutions and our eliminations. Instead of looking at nucleophiles, we now need to look at bases. When we shift to the elimination, or at least E1, you'll notice that we say a weak base, but heat is kind of a signifier for an elimination reaction. Okay, why do we want a weak base? Well, do you see base written in any of the E1 mechanism? It's not there. Okay, so we don't need a base. The next aspect that's important to recognize is that while we don't need a base, we also do not want a nucleophile. Because if a nucleophile is present, we don't get the E1, we'd be getting the substitution. Remember, it's SN in our substitution mechanisms, N for nucleophile. There is no N in an elimination, because if there is a nucleophile, everything gets ruined. Okay, so we want to be thinking about bases when we're looking at our eliminations. Solvent, we want a polar protic solvent. Okay. This should immediately kind of be sending off some alarm bells, because if I went through and just provided what we had here and erased all of this, okay, what type of mechanism does this one start to look like? It starts to give you the conditions for an SN1 reaction. That's a bit dicey. Okay, so one of the issues that you'll find is going to happen with your E1 mechanism is it is going to compete with your SN1. As far as your regiochemistry and your product, we get mainly the trans product, and that's because that forms the more stable double bond. Okay, we've got the trans product. The other aspect that comes out of that, whoops, pushed the wrong button, is that we get the Zaitsev product favored. We want the most stable double bond, so we'll eliminate such that we form the most substituted double bond. Whoa, hey now. Sorry about that. So we want our Zaitsev product. Okay. As far as complications go, we've got rearrangements, we have potential resonance contributors, and that's all because we form the carbocation. And then, as we just said earlier, this directly competes with the SN1. Okay, so how do you know you're going to run an elimination, and particularly an E1 elimination, over a substitution? Well, we just mentioned the two big signifiers. Okay, we have a base instead of a nucleophile, and we see heat. Okay. Or rather, we see a lack of a nucleophile, a strong nucleophile. So really the only thing that tips us off that we're looking at an elimination versus a substitution as far as E1 and SN1 goes is really just the heat. Okay. So if you see heat, probably doing an elimination. It's not a guarantee, but it's your most likely bet at that point. More than likely, what's actually being asked is for you to provide multiple products, and you should be providing both the E1 product and the SN1 product. Okay, that's just obnoxious, but that's what you have to go through and deal with because these mechanisms react with each other, which is one of the reasons why a synthetic chemist will avoid, like the plague, any elimination or substitution reaction that follows under the unimolecular mechanism, because it makes a mess out of the possible products. Okay. When we move to the E2, sorry, I thought this was going to stepwise through it. Everything happens in one fell swoop. Okay. And because everything happens in one fell swoop, I need something to help break that hydrogen off. So one of the big things that needs to be present is that base with its strong electron density to help remove that hydrogen to force the leaving group off. So the E2, the leaving group gets forced off. In the E1, the leaving group just pieces out and takes off on its own. So, as far as your substrate characteristics, what we're focusing on is what makes the most stable pi bond. So in E2, your substrate will actually favor your tertiary and secondary over your primary substitution patterns. And that is because a tertiary substrate is going to give you a more stable end product. It's going to be more substituted than, say, a primary substrate. Okay, so it's a big difference between the E2 and the SN2 as far as the bimolecular reactions go. So that is an important one to grab a hold of. Leaving group, again, needs to be good. Biggest aspect out of the E2, you need a strong base. Okay, and that is because the leaving group can't leave on its own because it doesn't leave a stable carbocation. So a base needs to come in and force the leaving group off. Okay, this step is really, really important. The leaving group has to get pushed off by that base removing a hydrogen. Okay. As far as the solvent goes, I would really ignore the solvent when you're looking at the E2. It is very misleading to look at it. It is nearly always protic. Okay? And that is just because of where we're getting the base from. So don't stress on the solvent when it comes to the E2 mechanism. As far as our regiochemistry, this is dictated by the alignment of the leaving group and the hydrogen. Okay, so this was one of the big complications out of Chapter 8. Depending on the arrangement of our hydrogen in our leaving group, we can get the cis or we can get the trans. Okay, it's very rare to get both under the E2 mechanism. The only way that can happen is if we have two possible hydrogens that align perfectly with the leaving group. Okay, so it is commonly a cis or trans that is specified from the anti-periplanar alignment of the leaving group and hydrogen. So let's go ahead and tag that in here too. We've got anti-periplanar. And then we most commonly favor the Zaitsev product. Your Zaitsev is the most substituted product. Okay? You can get the Hoffman, look at the details of the Hoffman later. It's a relatively small amount. So our complications, we have to have that anti-periplanar alignment, and we have the potential for the Hoffman elimination, meaning the least substituted double bond. To get your Hoffman elimination, you're looking at a very sterically hindered base. Okay. And a sterically hindered leaving group. Both those conditions are satisfied, you are going to be looking at the Hoffman product, which means your least stable double bond or your least substituted double bond. Okay. So E1 versus E2, we're kind of pushing through our systems, and both those we're really kind of pushing towards the most stable product. We get a slightly different phrasing when we look at the substrate for your E1 because we're really looking at the cation. As far as the strength of the base, we want a strong base in the E2, and we don't really care in the E1, which by definition means it's going to have to be a weak base. Good leaving group, as always. Substrate pattern, you'll notice in both of these we're looking at tertiary substrates being the one we want. This is because the tertiary substrate is necessarily going to lead us to the Zaitsev product, okay, which is our most stable product in both circumstances. Okay, so that is a big departure from the SN2 reaction. Solvent plays a really minor role for ultimately both of these. In the E1, it is officially the polar protic solvent because you need to stabilize that carbocation. Okay. As far as your stereochemistry goes, you're looking at cis or trans possible for the E2. For the E1, you're looking at just the trans product being your primary product. Okay. So, how do you predict? So, given a reaction, how do we know which one is actually going to be our option? So, your textbook has kind of come up with this neat little table option. I'm kind of surprised I hadn't thought of it before because I pushed a big table option for spectroscopy. But, you know, beside the point, neither here nor there. I do kind of debate their choice of terms putting on the side. So let's kind of evaluate those. What I would do is go through and call this substrate and then I would look at nucleophile. I would probably add another one for base, so differentiating between the nucleophile and the base. Nucleophile, base, substrate, and then solvent. And that is how I would set this up. I would not include the leaving group because they all need a good leaving group, so it's kind of a moot point to include that. It's just providing it so you can check off boxes. Concentration, I find, is kind of an odd statement, so I don't quite know what that's actually referencing. And then they don't really provide any reference to the substrate stability. So if we go through any given condition, we can then evaluate these probabilities. So how would I address this? So let me go through with the reaction shown. Let me erase their tick marks. Okay, we'll sort of erase their tick marks. And evaluate the above reaction. So I look at the substrate. I got a secondary substrate. Secondary substrates suck because that works for all of them. Okay, so that didn't help me out. Next part. I would immediately look and recognize that I have bromide, not just sodium, but bromide, which is a twofold process for me, because number one, that tells me I don't have a base, okay, which means I can't check off elimination reactions, but I can now check off nucleophile sections, and I'll be checking off the SN2 because that is a strong nucleophile with that negative charge. And in the base one, I could almost just cross out, okay, because it's not a base. Okay. Next part is I could then move to the solvent. I would actually make the argument that there is nothing that any one of those other reactions could really do to kind of win out and now all of a sudden dominate and win the overall points, I guess, if you will, for an SN2, to beat out the SN2. And that's because the solvent plays a relatively minor role in the overall reaction. So I'm not going to use the solvent to say it's equal in weighting to all the others. But we can go ahead and take a look at the solvent anyway. You'll notice that they just abbreviated. This is something that I'm sure you aren't going to like, but officially you need to know what those abbreviations mean. That abbreviation means we have dimethyl sulfoxide, which is going to be even more fun for you because now, of course, I'm going to tell you that you need to know how to turn that into a structure, which is this guy. You've got the two methyls on the sides, and then you have the sulfoxide in the middle. And when we look at that structure, what we have here is a polar aprotic solvent. Still checks off the SN2. I would say we're looking at 3 to 1s on all the other. We're looking at an SN2 reaction occurring here. So now if I wanted to go through and predict my product, I'm number one going through and doing a substitution reaction. So I'm going to take my main structure here and I'm doing a substitution for bromide being my new piece on here. Because it's an SN2 reaction, I now have to consider stereochemistry. And I look at my material and I say I got 1, 2, 3, and there's a hydrogen, 4 different groups, so crap, I have to worry about stereochemistry. So now I got to think back to the complications of the SN2, and in the SN2 it has to do a backside attack, which means the nucleophile is going to come in from the complete opposite direction of the leaving group leaving. The opposite direction of that chloride is going to be behind, so dashed, and I now have my product. So what I'm doing to evaluate these things is going back through and checking off all these little boxes in my head, saying, okay, these are the things that are contributing. Now that I know the mechanism, I can predict the product. Okay? So this is kind of your process that you need to be working through when you think through these kind of problems. So, questions that run through my head. I usually start with the strength of the nucleophile because that's going to determine the order of the reaction. If it's a strong either nucleophile or base, I'm looking at the E2 or the SN2 reactions. I'm immediately in bimolecular, so I can eliminate my one-type reactions. Remember the big difference between nucleophiles and bases. They both ultimately donate electrons, but it's a question of what they donate electrons to. Your nucleophiles, very little sterics. Your bases, sterics are okay. Okay? So be aware of those kind of subtle differences. Bulky bases will favor the elimination because they can't do substitution. So if I look at my nucleophile and or base and I say that's bulky, immediately I'm jumping on the elimination train and I ignore everything else. Substrate structure is usually the next thing I'll move to. And the reason why I don't do substrate structure first is that if we look at our overall possible substrates, primary, secondary, and tertiary, primary is the only one that allows me to decide I'm doing an SN2 reaction most probably. Okay? If it's a secondary halide, I'm kind of screwed because all mechanisms are valid for a secondary halide. And then a tertiary halide, I'm going to get a mixture of 3 of these possible mechanisms. Okay, so the substrate structure doesn't help me as much as identifying if I'm looking at a strong nucleophile or base. The last thing I typically look for would be high temperatures, okay, because high temperatures tend to favor elimination. It's not going to say, oh, this is a hot reaction, but what you'll see will very typically be a delta symbol referencing that heat was added. So you might see a delta. The other thing you might see would be 100 degrees Celsius, because 100 degrees Celsius is hot. Another thing that you might see would be 0 degrees Celsius. Okay, well, 0 degrees Celsius is cold. That is actually saying that I want to do a substitution reaction, not an elimination. Okay, so we can add heat or we can not add heat, as the case may be. We're starting to get close to the end of the lecture here. I'm not sure exactly where it ends, so we may stop kind of mid-lecture. So again, we've got yet another summary where now we have everything on one side, looking at each of those individual reactions and the things that kind of contribute to them. These are things you need to know, like immediate, I've got it, move on, I've got it, move on, so you can start to predict and draw out your products. And your complications, in the SN1, you move to a racemic product. Okay? The other big complication with the SN1 is you are simultaneously competing with the E1. So very commonly under SN1 conditions, you're kind of being asked to provide both the substitution and the elimination. So be aware of that complication. For the SN2, you get inversion of stereochemistry. So if you started R, you go S. If you started S, you go R. In the elimination type reactions, if you're looking at an E1, you get mostly the trans alkene, which is actually less of a complication and more of a bonus because we don't have to think about it as much. You'll get the Zaitsev product exclusively, so we'll always form the most stable double bond, which is actually kind of nice for those both two. The actual complication that comes out of the E1 is that it is simultaneous with the SN1, so you have to watch out for those types of reactions. In the E2, we have to have that anti-periplanar alignment. So, and you really can see that from your Newman projections, which is why we talked about Newman projections at the beginning of the semester. You can have a cis product come out of the E2. Okay, so you'll notice I'm saying cis possible, I'm not saying it's always cis. Very commonly it's either cis or trans, and it's exclusively one of those. Whereas in the elimination, you get a mixture. You get both cis and trans, but it's mostly the trans because that's the more stable one. In the E2, you typically will get the Zaitsev unless the Hofmann conditions have been satisfied for those Hofmann products, which again tends to be fairly rare, but it does pop up every so often. The rest of these slides, actually now that I think about it, are examples that you can go through and work. So one thing to be aware of is that we can do a double elimination to form alkynes. We just have to have the proper conditions for it. And it's going to end up running two elimination reactions. Not simultaneous, but first one elimination, then the other. Okay. One of the issues with these is that you end up forming an alkene intermediate. Okay. So if we draw off that top one, we end up with probably something along these lines. Whoops. You would probably end up with this guy. Okay. Well, to do the elimination here, we have to be able to remove that carbon-hydrogen bond to force the leaving group to leave. You'll notice that we absolutely cannot do an E1 elimination because we cannot form a stable carbocation. So we need something to help remove that hydrogen. But remember, your alkenes aren't particularly acidic, so one of the things you'll notice that if this is going to happen, we have to use a really, really strong base. Under these conditions, what we're using is sodium amide. That is a stronger base than sodium hydroxide. Okay, so we need that strong base to go through and do the alkyne formation. So that's our first, like, reagent, oh my gosh, I have to know the reagent problem. Okay, you need sodium amide to go through and do these. Another term that might pop up is this idea of vicinal and geminal that I always get backwards because it's a nomenclature thing. Vicinal, I believe, oh shoot, I don't remember. Look it up. Vicinal and geminal are in reference to these types of halogens. One of those is vicinal and one of those is geminal, and in all fairness, I really honestly can't remember what it is. You may see those terms pop up. It's not something that I typically use because I can't remember them. But be aware that those terms might pop up, so it's a good thing to look for. Intermolecular versus intramolecular. Oddly enough, we've actually already done this, so I don't know why that made it into these slides. When we're looking at substitution reactions, we can do intermolecular reactions. I mean, that's our standard one. Under these circumstances, we probably wouldn't get this as your product, and that's because an intramolecular reaction is probably going to be favored because you form a six-membered ring. Okay? And that six-membered ring is relatively stable, so you'd probably end up seeing the intramolecular reaction happening. How do you know that you need to be doing intramolecular? Well, as we talked about at the tail end of Chapter 8, if you are forced to do it, I draw you a product where it is a ring, then you need to do it. The other option is, as we're now finding out, if you form a stable product, it is very likely that you should do the intramolecular instead of the intermolecular reaction. Okay? And that stable product usually means a six-membered ring. It can happen with five-membered rings as well, but the six-membered ring is the big tip-off. After that, we've got a bunch of reactions. So here are some reaction conditions. While I'm talking over this, feel free to pause at any point because I'm not going to draw out any of the answers for these. I'm going to leave you guys to go through and solve them, and then you can ask questions about them later if you would like. With this question, or with this set, assume it's an SN1 reaction. Okay, so we're going back to kind of the Chapter 8 stuff. I'm telling you, these are SN1. Make sure everything you do shows products as SN1 products. Okay. After you do that, you can go back and say, hey, what was he talking about? Because these aren't SN1 reactions. You're right. Most of them are not SN1 reactions, but that's beside the point. Okay. Assume at this point that they're SN1. The next slide, assume that they're SN2. Okay. All of these do happen to be SN2, so that's not a problem. So just think about how you would approach each of these questions under SN2 conditions and make sure that you satisfy those requirements. You'll notice that there are very similar problems both within this set and the previous set. Okay? So I'll give you a second to click pause for the SN1, and I'll give you a second to click pause for the SN2. And then we are done exactly in an hour. Awesome.